The essential things often do not hit our dull senses the easiest. We see the shell first. To the undeveloped mind, matter is all there is. But when we look deeper into life, we realize the fact and the importance of spirituality, the sense that reason, emotions, the joys and pains, they have nothing to do with things, and the ties that bind man to the infinite are all permanent elements of life. Quote from Cope. This series of lectures has been inspired by the consideration I expressed in the introduction to the fundamentals. An awareness of the fundamental questions of quantum physics is now essential if we get closer to understanding the workings of our organ systems involved in homeostasis. We do not need to become quantum physicists. Still, we need to be aware of scientific thinking and how it can become disinformed by the activities of various interest groups. Below, we present a variety of historical events and scientific concepts, mainly quoting scientists who have received significant accolades and have demonstrated that their voice on scientific issues is not averaged but carries more weight than the scientific community at the time can grasp and accept. We have compiled this treatise primarily from quotations, quoting the ideas of scientists who have committed themselves to the knowledge of reality. The introduction to the topic is based on a lecture given by Ruben Laszlo on the occasion of his honorary doctorate at the University of PH. Ruben Laszlo writes about today's scientific approach. At the beginning of the 21st century, the scientific worldview is changing significantly. In the early 21st century, science is undergoing a profound change, just as it did at the beginning of the 20th century, when Einstein replaced Newton's harmonious but mechanical clockwork universe with a relativistic universe. However, the concept that has now emerged at the sharp edge of the natural sciences, in the new physics, the new biology, the new psychology, and psychotherapy, is not common. The image that most people call scientific is now obsolete. From a general point of view, science offers a dehumanized view of the world, a dry and abstract picture made up of numbers and formulas. The universe is like a soulless mechanism, and life in it is a random event. In the new conception, the universe is not a lifeless, soulless assemblage of motionless bits of matter. Still, it is more like a living organism than a dull rock. Life is not an accidental event, and the elemental driving forces of the human psyche include more than just sex and complacency. A new concept of matter and space. The change in how science sees the world is already reflected in the most elementary concepts of reality, matter and space. Western thought has consistently held that matter and space exist together and are the ultimate constituents of reality. Matter occupies space and moves in it. Space is something like a background curtain or container. This classical notion was radically reworked in Einstein's relativistic universe, where spacetime became a complex four-dimensional manifold, as in Bohr and Heisenberg's quantum world. This is now being rethought in the light of scientists' exploration of the nature of the quantum vacuum, which is beginning to show that this energy field, which underlies the whole of spacetime, no longer supports the view that matter is primary and space is secondary. Primary reality must be attributed to space or the quantum vacuum's cosmically extended zero-point field. The shift from matter to energy as the primary reality is the discovery that, despite its name, the quantum vacuum is not empty space, aka not a vacuum, but saturated space, aka a plenum. This is the focus, or location, of the zero-point field, whose name derives from the fact that the energies of this field are revealed when all other energies disappear in a particle of the system, the zero point. In itself, this extended field is not electromagnetic, gravitational, or nuclear. In contrast, the quantum vacuum, quantum plenum, is the resultant source of the known electromagnetic, gravitational, and nuclear forces and fields. It is also the source of the matter particles themselves. If the zero-point field of a vacuum is stimulated with sufficient energy, on the order of 10 on the 27th erg/cubic centimeters, a region of it will be ejected from its negative energy state into a positive energy state. This results in pair creation, a positive energy, fundamental, particle emerges from the vacuum. In contrast, a negative energy, virtual, particle pair remains inside. The energy density of the zero-point field is almost inconceivable. According to John Archibald Wheeler, it goes up, based on Einstein's mass-energy equation, E equals m-fold c squared, to 10 on the 94th grams/cubic centimeters. A density of 10 on the 94th grams per cubic centimeter is unimaginably more remarkable than the total mass density of the universe, which is no more than 10 on the 29th grams per cubic centimeter. Otherwise, since energy equals mass and mass always carries gravity, this overcompressed universe would immediately shrink to a size smaller than the radius of an atom. Is it reasonable to look at matter today as a product of the zero-point field of a vacuum? This emerging concept has no absolute matter but only an absolute matter-generating energy field. Although this interpretation of matter and space seems to turn common sense thinking on its head, closer observation shows that it is closer to everyday assumptions about the nature of reality than the standard ideas of 20th century physics. The abstraction that boggles students' minds in introductory physics courses is no longer a problem. Light and gravity are no longer phantom-like waves traveling through empty space. As Laszlo Gzdg showed by reforming Einstein's general relativity equations, time-space is not only a geometrical reality but also a physical reality. It is a matter, a saturated medium of virtual energy that can be stirred and excite patterns and waves. Light, like sound in the air, is a wave traveling in this constant field of energy, and tables, trees, rocks, swallows, and other seemingly solid objects are nothing but standing waves in this field. The whole range of interactions between the vacuum and the micro and macro world has been investigated by Russian physicists with considerable success. According to Akhinov and his colleagues' torsion field theory of the physical vacuum, objects from quanta to galaxies create vortices in the vacuum, that is, they spin in the cosmic ether. These torsion waves are persistent, they can persist even without the objects that generate them. The existence of such torsion wave phantoms in living tissue has been confirmed by experiments by Vladimir Poponin and his team at the Institute of Biochemical Physics of the Russian Academy of Sciences. Poponin, who replicated the experiment at the HeartMath Institute in the U.S., exposed a DNA molecule sample to a chamber-controlled temperature and a laser beam. He found that the electromagnetic field around the chamber showed a particular structure, more or less as expected. However, he also noticed that this structure persists after the DNA itself has been removed from the laser-irradiated chamber. The DNA trace in the field is still present when it is no longer there. Poponin and colleagues concluded that the experiment suggests a new field structure has emerged from the physical vacuum. They say the phantom effect manifests a previously unnoticed vacuum substructure. Through interactions with the zero-point field of the quantum vacuum, the organism is in a tenuous but effectively reciprocal relationship with the environment. Like the universe itself, life evolves in a sacred dance. This means that living organisms are not individuals in some kind of leather and that the living world is not the bumpy field of classical Darwinism, where everything is fighting against everything else, bellum omnium contra omnes, with all species, all organisms and all genes competing for advantage. Living organisms are part of a broad network of intimate relationships that spans the biosphere, and is part of an even broader network of relationships that reach far into the cosmos. Formations of the human organism, such as mind and consciousness, are embedded in a network of relationships. It follows that the information provided by the brain about some features of the world beyond our skulls is not limited to the visible spectrum of electromagnetic waves nor to the audible spectrum of sound waves but extends to the wave fields in the zero-point field of the vacuum. The transport between our consciousness and the rest of the world is constant and works in both directions. Everything in our minds leaves wave traces in the surrounding vacuum field, and the subtle patterns transmitted there can be perceived in the right state of consciousness. This exciting idea is supported by children's experiences, people of natural cultures and people in altered states of consciousness. These latter states of consciousness include dreaming, imagination, creative ecstasy, mystical delirium, deep meditation or prayer, hypnosis, and states of the brain and mind that occur in the halls of death. Since Elizabeth Kubler-Ross's classic studies, clinical psychologists and researchers in the field have regularly studied near-death experiences, NDEs. It appears that those who experience near-death have significant experiences that have a pronounced memory component. JN. According to Raymond Moody, it is now abundantly clear that the experiences of many people who have been resurrected from near death are very similar from case to case, regardless of the patient's age, gender, religion, culture, education, and socioeconomic background. Reminiscence, a panoramic replay of a lifetime's experiences, is much more widespread than is generally acknowledged. According to the 1982 survey by the Junior George Gallup, about 8 million adults in the U.S. alone have undergone it. 32% of the people surveyed said that view back from their live stream was part of their near-death experience. Ruven Lazo writes of the complications unfolding in the physics of our time. At the dawn of the 20th century, the pure atomistic and deterministic picture of classical mechanics became somewhat confused. The problems began when, in the early 19th century, the English chemist John Dalton rediscovered the atomic theory of Democritus. The English scientist's theory that all gases are made up of tiny and indivisible individual units called atoms revolutionized chemistry. But his triumph proved short-lived. 50 years after the publication of Dalton's theory, experimentalists discovered that atoms are not indivisible but are made up of even smaller particles, and even these cannot be the ultimate atoms as the Greeks knew them because they must be even more divisible if they are finite in space. Indeed, once researchers had huge experimental facilities, atoms and even nuclei could be split apart. When the 19th century atom and the 20th century nucleus split, more than just physical matter fell apart. The whole edifice of classical science shook. The experiments of early 20th century physics overturned the view that reality was made up of indivisible atoms. However, physicists had not yet been able to propose any unified and meaningful concept to replace it. The idea of matter itself came into question. The subatomic particles that result from the splitting of atoms and nuclei do not behave in the same way as the traditional solid bodies. They have some mysterious connection, some indeterminacy. Moreover, these particles have a dual nature. They behave as waves and particles. By the 1920s, researchers were confronted with a new world of quantum physics in which the strangeness of physical reality surpassed all expectations. Space and time, instead of being a humble background to the interaction of material atoms, or points of mass, became a complex existence, interacting with photons and electrons and penetrating the web of physical phenomena. To philosophers and philosophically minded scientists, the physical universe itself seemed to become immaterial. In the words of Karl Popper, matter is more cloud-like than rock-solid. The revolution in quantum physics that unfolded in the 1920s brought about much more profound changes than had happened to relativistic physics at the turn of the century. Einstein's approach retained Newtonian physics's unambiguous description and fundamental determination characteristic. On the other hand, quantum field theory discarded unambiguous trajectories and built probable indeterminacy into the foundations of material reality. Thus, the domain of matter became increasingly mysterious. Reality independent of us seemed to dissolve before the wondering eyes of quantum physicists. Seeing the mysteries of nature, many physicists, with the Danish physicist Niels Bohr at the forefront, decided to stop thinking about the independent nature they observed and regard the objects of their observations as mere phenomena. As the German physicist Werner Heisenberg observed, all phenomena are not works of nature but merely fabrics of science. The atomic physicist, Heisenberg said, must be content with the fact that his science is only one eye in an endless chain of debate between man and nature, but cannot simply speak of nature as such. We are dependent on language, Bohr insisted. Physics is about what we can say about nature. According to Sir Arthur Eddington, the external world of physics has become a shadow world. Nothing is real, he writes, not even our own wives. Quantum physics lulls the scientist into believing his wife is a complicated differential equation. Eddington added that one is tactful enough not to voice this opinion much in family life. Although it is not advisable to speculate about the nature of reality beyond laboratory observations, some researchers have ventured further. They believe that the world to which the language and texture of science refers is mental rather than material, spiritual rather than material. To put the conclusion crudely, Eddington said, the thing of which the world is composed is more mental than material. Sir James Jeans argued, the combined evidence of the various pieces of probable reasoning makes it increasingly likely that this reality can be regarded as more spiritual than material. The universe is somehow more like a vast thought than a vast machine. Heisenberg regrets the fallacy of the philosophical doctrine of Democritus. According to him, the world is a mathematical rather than a material structure. It is not worth asking what the formulas of mathematical physics refer to apart from themselves. Just as Plato resolved the materialism of the ancient Greek natural philosophers in an abstract world of forms and ideas, the definite world of classical mechanics disappeared in the complex formulae of mathematical physics. Researchers could fail to identify the fundamental entities behind the diversity of apparent phenomena and needed help deciding whether such entities existed in nature. Clearly, neither the Democritus atom nor the Newtonian center of mass is the ultimate basis of physical reality. In the words of the Hungarian-born American atomic physicist Jenő Wigner, modern quantum physics has to be content with working with observations rather than observables. Physicists can describe what they observe but are not so good at relating their observations to real things that exist independently of observation. This situation was not fortunate, nor was it accepted by all. The questions that confronted quantum physicists in the laboratories sparked the most famous and profound debate about the nature of physical reality in the history of modern science. Between 1927 and 1933, Albert Einstein and the founder of quantum physics, the Danish physicist Niels Bohr, met and corresponded at length about interpreting the perturbing observations. Einstein could not accept the particular indeterminacy that characterized the behavior of elementary particles. He devised a succession of so-called thought experiments to show that quantum theory, as it was then formulated, was logically inconsistent. On the other hand, Bohr rejected any interpretation that exceeded actual observation's limits. According to the Danish physicist, nature had set absolute limits to what could be measured and observed and what could be clearly stated. Einstein agreed with Heisenberg's indeterminacy principle, namely that an elementary particle's position and momentum, cannot be measured simultaneously, but he no longer accepted that this meant that elementary particles had no definite position and momentum. Bohr argued there was no point in talking about a particle with a given orbit if there was no observer or means to record it. This was unacceptable to Einstein. If a person, say a mouse, looks at the world, does that change the state of the world? Einstein asked the American physicist John Wheeler at his relativity seminar in Princeton. I find this idea intolerable, he wrote earlier to Max Born. If today's interpretation proved correct, he continued, I would rather be a shoemaker or a toy cave employee than a physicist. At the end of his dialogue with Einstein, Bohr confined himself to the term quantum phenomenon. As the American physicist John Wheeler later pointed out, this term is highly significant. It suggests that when we talk about a particle, we are not discussing a separate reality independent of the observer. There is no basis for claiming what particles are like or what they do between two observed signals of emission and arrival. In Wheeler's illustrative phrase, what happens in the meantime is like a big foggy kite. You can see its tail where the particle exited and its mouth biting into the sensor, but its body is just a blur. The quantum phenomenon, Wheeler said, is the strangest phenomenon in this world. Most quantum physicists today accept that the strangest among all phenomena is that all their formulas, the pride of 3 generations of famous researchers, perform their assigned tasks. If research implies questioning the validity of the fundamental formulas, physicists usually dare not search for a deeper reality. After some 20 years of research and exploration, Quantum theory today can boast astonishingly successful and desperately confusing. Thousands of physicists have used the formulas to explore the subatomic world in almost every conceivable experiment, and their results have proved remarkably consistent. However, there are significant gaps in the knowledge that any sound mind accepts as reality independent of the observer. On the one hand, for example, quantum theory cannot describe the essential components of everyday objects as elements in those objects. Common sense speaks of unimaginable probabilistic entities present simultaneously in a given place that are nothing more than waves or particles, depending on the question we ask them, and our mutual relationship with them. On the other hand, quantum theory does not explain one of our most basic intuitions, that time is irreversible. In the framework of quantum equations, the irreversibility of time is a haunting nightmare and, in the view of John No Njmn, a consequence of our measurement activities. In the subatomic world, Erwin Schrödinger's equations for the quantum state of particles cannot distinguish between past and future, just as Newton's equations of motion cannot do so for macroscopic bodies and processes. Time enters the mathematics of quantum theory only when the essentially probable but quasi-unimaginable state of particles passes into a definite state that is already familiar to us from our everyday relations with reality. That is when the superimposed wave-like phenomena that defy common sense collapse into a state that can be determined by common sense. But this collapse, together with a series of superposed probabilities that contradict common sense, is not the face of reality independent of our observation. We must attribute it to our interaction with reality. According to John No Njmn, it is because we measure the particle, and according to Jenno Wigner, it is because our knowledge of the particle interacts with us. We could continue with this fascinating treatise if we needed a more tangible task. I want to bring concepts into a common wavelength that can make the wave nature of the endocannabinoid system more comprehensible by keeping a vigilant watch on our world. For example, a critical mechanism in the unseen world is the phenomenon of magnetism. There are charged molecules that attract or repel each other by their charge. All in all, this is what makes bees pollinate. The charge of the bees attracts the pollen, which they then convert into honey in the hives. Still, they also pollinate the flowers, which is vital for our lives because it produces edible foods. Another example of the importance of the charge is the specific protection of venomous snakes from snake venom, their own venom. The snake venom is molecularly charged, making it easier to paralyze the prey. Still, at the same time, their own nervous system receptors are oppositely charged, so they repel the venom. Everyone knows that magnetism describes the presence of attractive and repulsive forces in a given space. I want to talk about the space in which every particle present is subject to the force that creates magnetism. Let's put a horseshoe magnet under a sheet of paper on which we sprinkle iron powder. We see that the iron dust particles are arranged in a regular pattern. We see this, but what we need to see is more important. It is valid for all particles that they can take on a similar pattern depending on their affinity. So for the molecules of air, if we put our hand in the horseshoe, it is valid for every particle of our fingers that the atoms, ions, molecules in our cells are also arranged according to the magnetic field within their own boundaries. MRI is based on this phenomenon. A high-energy homogeneous electromagnetic field is induced, which forces the protons into a uniform position. Then, the field is deliberately collapsed to see how the protons return to their resting position, the state they were in before the excitation. This can be used to distinguish bones and soft tissue, for which imaging software has been written. If people were not primarily interested in appearances, creating software for the vitality of tissues would also be possible, which is a much more exciting question regarding reality. A separate lecture will discuss the physical basis of MRI, both in terms of diagnostics and some of the terrestrial devices based on this phenomenon. They tried to understand the magnetic force. The research led to quantum physics. However, as with everything else, the theories accepted today have given highly questionable answers to many questions. The answer, however, has long been found. at least in the right place, many times in history. Let's review the historical events objectively, but now with an emphasis on those that have been deliberately overlooked in the last century. Since the 19th century, the science of our modern civilization has begun to use the changed concept of the atom as the smallest part of a chemical element. In 1897, thanks to the English physicist Joseph John Thomson, who found that cathode rays are produced by the flow of the tiniest particles, the electron, the carrier of the negative elementary electric charge of atoms, was discovered. In 1919, the English physicist Ernest Rutherford discovered proton, a positively charged elementary particle, due to research into nuclear decay. In 1932, the English physicist James Chadwick discovered neutron, an elementary particle that is part of the nucleus of an atom, with a mass close to that of the proton but without an electric charge, while researching the interaction of alpha particles with beryllium. In modern science, there are still unresolved questions about the description of the internal structure of the nucleus. The hypothesis that there is a photon in the electromagnetic field was described in 1900 by the German physicist-theorist Max Planck, the founder of quantum physics. In 1905, Albert Einstein, working on Planck's idea, hypothesized that electromagnetic radiation, light, is nothing more than a flux of separate quanta, photons. American physicists Robert Millikan from 1912 to 1915 and Arthur Compton from 1922 obtained direct experimental proof of the photon's existence. In 1930, the Swiss physicist Wolfgang Pauli hypothesized the existence of an elementary particle that interacts with matter almost entirely, followed in the mid-1950s by American physicist Frederick Reines experimentally confirmed the existence of a neutral, stable particle, the neutrino. From the 1930s until almost the early 1950s, research on elementary particles was closely linked to research on space beams. From the 1950s to the present day, accelerators have been the main tools for research on elementary particles in physics. In contrast, new elementary particles created by the collision of accelerated protons and electrons with matter have become the object of study. Since then, many different particles have been discovered, including unstable elementary particles, volatile particles called resonances. For example, the first of these was found in 1953, D1, heavy antiparticles, antiproton, in 1955, antineutrinos, in 1956, anti-sigma hyperons, in 1960, and so on. The diversity of properties of the particles discovered was unexpected by scientists. In studying this question, they had to add characteristics such as electric charge, angular momentum, strangeness, charm, etc. It became clear that the world of elementary particles differed considerably in its laws, properties and behavior from the traditional views of it based on the ideas of classical physics. I would also like to present another aspect of history, citing the work of the Al-Ra International Public Movement. It is a global coalition founded in 2011 by scientists, free of the global interests we know today.